Okay, we continue with one example. Here we want to derive the equation of motion for this system, which consists of a rigid bar, and we want to find the steady state solution of this system subjected to this moment m naught cosine omega t. As you can see, this is a harmonic excitation about range O, and the data is the stiffness is 5000 Newton per meter. We have two springs with stiffness each 5000 Newton per meter. The total length of the bar is 1 meter. The mass of the bar is 10 kilogram. M naught, or the amplitude of the excitation, is 100 Newton meter, and omega, which is the frequency of the excitation, is 1000 RPM. First of all, uh, I should mention that we need to convert the frequency from RPM to radian per second. So let's start by extracting the equation of motion for this system. As you can see, this is a rigid body. We can use the Newton's second law to extract the equation of motion for this system. And for this purpose, we need to consider an initial motion and plot the free body diagram for the system, similar to the dynamics problem. And then we can write the Newton's second law equation for the moment equation, for example, about this point O, and extract the equation of motion. So if we plot the free body diagram and we assume that this bar is rotating in counterclockwise direction, in positive direction of theta, as you can see, this is theta. This is the degree of freedom, theta. So when this bar is rotating in counterclockwise direction, the spring F1 will be pulled. So F1 will be in upward direction and F2 will be pushed. So the force due to this spring is in downward direction. And finally, the moment due to these two forces are in clockwise direction. So this is the free body diagram. Of course, we have two reactions here at this pin O, but because we are writing the moment about this point O, these two forces will not appear in the equation of motion. And also the weight, which is neglected, because the weight of this bar in static equilibrium condition will create some initial deflection in these two springs. So when we ignore the initial deflection in the springs, we also need to ignore the weight in the equation of motion, or in the Newton's second law equation. So if we write the Newton's second law about point O, the moment equation about point O, it must be equal to the mass moment of inertia about point O theta double dot. So this is the right hand side of the equation, which J sub O is the mass moment of inertia about point O, and we can find it by using the mass moment of inertia about the mass center. The mass center for this bar is located at its center. So the mass moment of inertia about point O is equal to the mass moment of inertia about the mass center, point G, plus m d squared, which d is the distance between point G and point O, and it's equal to L divided by 4. So this is the mass moment of inertia about point O, and we can insert into the Newton's second law here to extract the equation of motion. Then in the left hand side of the equation, we have the moments about point O. We have two forces, F1 and F2, and also we have one external force, the moment, which is a harmonic moment. As you can see, the moment due to F1 and F2 are in clockwise direction. So we will have one negative sign for these moments because the counterclockwise direction is the positive direction for theta. And also the moment m naught cosine omega t, which is in counterclockwise direction, it will be positive. So this is the moment of the external moment. And the moment due to F1 is equal to F1 times by its arm, which is L over 4. And the moment due to this force F2 is F2 times by its arm, which is 3L over 4. So, and we have one negative sign, as I told you, because of the direction of the moment. And now we can simplify this equation. And also we need to substitute F1 and F2, which F1 is k times by deflection of this point, which the deflection or displacement of this point is equal to L over 4 times by theta, and the deflection of this point, which F2 is equal to k, the stiffness of the spring, times by the deflection of this point, and the deflection is equal to 3L over 4 times by theta. So we can substitute and find for F1 and F2. This is the F1 and F2. We can substitute into the first equation here and simplify, and finally we can extract the equation of motion in this form. So the next step, we need to substitute the numerical value for J naught, for KL, and for the external force M naught and omega, and then we can solve this equation. Any questions so far? Is it clear? Okay. So for this example, we need to obtain the steady state response, and which is the particular solution. So we don't need to obtain the homogeneous response, and only we will solve the non-homogeneous equation for the particular solution. So here we can substitute the numerical value. As I told you, we for J naught, for omega, which is 1000 RPM, and as I told you, we should convert it into radian per second. For this purpose, it should multiply by 2 pi and divided by 60. So from RPM to radian per second, we can use this term to convert from RPM to radian per second. And then we can substitute into the equation. So this is the equation of motion. If we wanted to extract the homogeneous solution, first we needed to obtain the characteristic equation, which was 1.458 times by alpha squared plus 3125 is equal to 0, and then we can solve this equation and obtain the homogeneous solution. But here we only need to obtain the particular solution or the steady state response. So we consider the particular response, which is called theta p. Here you can see that the non-homogeneous term is a cosine function. So the particular response must be considered a combination of cosine and sine with the frequency of omega, which omega is 104.7 radian per second. So theta pt is equal to C1 times by cosine omega t plus C2 times by sine omega t. And C1 and C2 will be obtained by substituting into the main equation. So for this purpose, we need to obtain theta double dot p, because into the equation you can see we have theta double dot and also we have theta. Let me use another pen. Okay, so here you can see this is theta dot. We can find the theta dot b, which is the first derivative of theta, the particular response with respect to time, The first derivative of this function is C1 times by derivative of cosine omega t, which is minus omega sine omega t, and the derivative of sine omega t is omega cosine omega t. So this is the first derivative, and the second derivative is, again, we should find the derivative of theta dot p with respect to time, and it's equal to, again, minus C1 omega is a constant value. The derivative of sine omega t is omega cosine omega t. So this term will be minus C1 omega squared cosine omega t, as you can see here. And the derivative of this term, which includes C2 and omega, which are constants. And we have the derivative of cosine omega t, which is again minus omega sine omega t, and we have another omega here, so it will be minus C2 omega squared sine omega t. So this is the second term. Now we can substitute theta double dot and theta. We will have 1.4 times by theta double dot, which is this term. This is theta double dot. Here I substitute, and plus 3125 times by theta p, which is here, and it must be equal to 100 cosine omega t. Now we can simplify this equation. In the left hand side, we have one term multiplied by cosine omega t and another term multiplied by sine omega t. It must be equal to 100 cosine omega t. So in the right hand side, we don't have sine omega t. So the coefficient of sine omega t must be equal to 0. Here you can see. And the coefficient of cosine omega t in the left hand side of the equation must be equal to 100, because in the right hand side the coefficient of cosine is 100. So this is the second equation. Now we can solve these two equations to obtain C1 and C2. From the first equation we can conclude that C2 is equal to 0, and from the first equation we can conclude that C1 is equal to minus 0.0077. Okay, so this is the steady state response, or the particular solution for this system. Clear? No question? And also we can use the formula to obtain this response, no difference. But as I always suggest you to use the theory of ODE and use the direct method to obtain the response, homogeneous or non-homogeneous. Okay, no question from this example? Is everything clear? No questions? Okay, so in the next section we want to investigate the response of a damped system under harmonic force. We can consider, similar to the previous section, we consider a harmonic external force like Ft, which is equal to F naught cosine omega t. Omega is the frequency of the excitation, and F naught is the amplitude of the external force. If you use the Newton's second law to extract the equation of motion, we can extract this equation, which is mx double dot plus cx dot plus kx. The homogeneous part is exactly the same as the free vibration equation. But in the right hand side of the equation, we have one non-homogeneous term, which is the external force, and it's equal to F naught cosine omega t. So according to the form of the non-homogeneous term, or the external force, the particular response will be considered in this form. As you can see, it's equal to the uppercase x, which this uppercase x in fact is the amplitude of the response, multiplied by cosine omega t minus phi, which omega is the frequency of excitation. Here, please pay attention that the frequency of the particular response or the steady state response is the frequency of the excitation, but the frequency in the homogeneous response is the natural frequency of your system. Of course, when we deal with a damped system, the frequency of the free vibration response or homogeneous response is the frequency of the damped system. So this frequency is very important. You should pay attention. In the particular response, it's exactly the same as the frequency of excitation. But sometimes we have the angle phase, as you can see here, phi, which is the angle phase. And sometimes this phi is equal to 0. It depends on the characteristic of your system. And here, because we have the damping and the viscous damping, and we have the term x dot into the equation, we have the angle phase. And you will see that one of the effect of this damper on your response is this angle phase. So this is phi or angle phase. And also, again, I should mention that you can consider the particular response similar to the previous example. You can consider the xpt in the form of, for example, C1 cosine omega t plus C2 sine omega t, and then you can find C1 and C2, which C1 and C2 are related to x, uppercase x, and phi. Okay. And one question here, what was happened if we have not considered the phi or the angle phase? As I told you, this is due to the x dot term into the equation. In previous section, when we deal with the force vibration of system without damping, and the equation was mx double dot plus kx is equal to f naught cosine omega t. Similar to the previous example, you saw that the particular solution was equal to x uppercase x cosine omega t, exactly the same as the external force. But here we have this phi, and this phi in fact will show the effect of the damping or the x dot term into the equation of motion. So to obtain x and phi, we need to plug into the main equation. You know, for obtaining the constant coefficient in the particular solution, we need to substitute into the main equation, similar to the example, and we can find the constant coefficients. Here, we have two unknowns, uppercase x, which is the amplitude, and phi, which is the angle phase. So we need to substitute into the main equation. The main equation is mx double dot plus c x dot. Here you can see this is the main equation. We need to obtain x double dot, x dot, and we have x, which is x cosine omega t minus phi, and then we can simplify. So we need to obtain x double dot. From this xpt, we can obtain that x dot is equal to the derivative of this term with respect to time. Uppercase x is a constant value, so the derivative of cosine omega t minus phi is equal to minus omega times by sine omega t minus phi. So the first derivative, or the x dot, is equal to minus uppercase x, which is the amplitude, times by omega times by sine omega t minus phi. And the second derivative of x with respect to time will be obtained from the derivative of this term with respect to time. Here we have minus x omega, which this term is constant. So the derivative of sine omega t minus phi is equal to omega times by cosine omega t minus phi. So x double dot is equal to minus uppercase x times by omega, and we have another omega from the second derivative, so it will be omega squared times by cosine omega t minus phi. So we can substitute x double dot, x dot, and x into the main equation here. And then you can simplify, you can extract this equation. As you can see, this is the equation of motion. By substituting the particular response, we will have in the left hand side, we have cosine omega t minus phi and sine omega t minus phi. But in the right hand side, we only have cosine omega t. So the next step, we need to use the trigonometry relation to convert cosine omega t minus phi into the cosine omega t and cosine phi, and also we need to convert sine omega t minus phi into the form of a combination of sine omega t and sine phi. So we use these equations. As you can see from the trigonometric relations, we know that cosine omega t minus phi is equal to cosine omega t multiplied by cosine phi plus sine omega t multiplied by sine phi. And also, we have sine omega t minus phi is equal to sine omega t cosine phi minus cosine omega t sine phi. So we need to substitute, instead of cosine omega t minus phi, we need to substitute this term. And also for sine omega t minus phi, we need to substitute from this term. So the next step, when you substitute these terms, in the left-hand side, you will have some equation multiplied by sine omega t and some equation multiplied by cosine omega t. And in the right-hand side, we have f naught times by cosine omega t. So you can, in the left-hand side, the coefficient of cosine omega t must be equal to f naught, and the coefficient of sine omega t must be equal to 0. So let's simplify this term. And you can obtain x and phi from these two equations. So by substituting and simplifying, you can obtain the amplitude of the response, as you can see, and the angle phase. Here, again, I should mention that when c is equal to 0, here in this equation, you can see when c is equal to 0, this term is 0, and the tangent inverse of 0 is equal to 0. So it means that the angle phase is 0, and the response will be exactly the same as for the response for the force vibration of undamped system. And also here, again, the amplitude this time will be 0 when c is equal to 0, or when we don't have damping. And the amplitude is the same as the previous section for an undamped system. Here you can see that if you plot ft and the particular response, the dashed line is the particular response, and you can see that we have one angle phase. And this angle phase is due to the damping in our system, and the period for xpt, of course, for here this is only the particular response. The period is similar to the period of the excitation because the frequency is the same. Okay, no questions so far. Is everything clear? Okay, so this is the response, and to substitute into this equation, you can also use the data from the previous section. You know that the natural frequency is the same. Omega n is the square root of k divided by m, which k, in fact, it's not the stiffness. This is the equivalent stiffness. I mean the coefficient of x into your equation, and m is the equivalent m. Let's back to the previous example here. I think it's very important. For example, here in this example, you can see this is the equation of motion, and this is the equivalent mass, and this term is the equivalent stiffness. I mean, this term is K and this term is M. When you want to obtain the natural frequency for this system, omega n is equal to the square root of K, which is 3,125 divided by the M, which is 1.4. And it's not equal to the K, the stiffness of the S-spring, okay? Because it's not a simple single degree of freedom system. This is a rigid body. Here you can see the stiffness of this system is K, and it's equal to, I think, 5,000. Yes, 5,000. So in this example, if when we ask about the natural frequency, please pay attention that the natural frequency for this type of system is not equal to the stiffness divided by mass, because the mass is 10 kilogram and the stiffness is 5,000. Most of the time in the problems in the exam, the students made these mistakes, and when they want to obtain the natural frequency for this system, they consider that the stiffness is 5,000. Here sometimes they consider we have two springs, so it will be 10,000, or sometimes they only consider K is equal to 5,000 and M is equal to 10, so the natural frequency is equal to square root of 5,000 divided by 10. And this is completely wrong, because it's not a simple spring mass system, and you need to obtain the equation of motion, and after that the coefficient of, here for example, because we have theta, because this is a rotational system, the coefficient of theta double dot is equivalent mass or equivalent mass moment of inertia, and the coefficient of theta or x is the equivalent mass moment of inertia, equivalent rotational stiffness or linear stiffness, okay, according to your motion. Here we have rotational motion, so it is equivalent rotational stiffness. If it was a translational system, it was a linear stiffness of the system. So we can write the response of course, the particular response of the system, or the steady state response of the system, in this form, as you can see, uppercase X times by cosine omega t minus V. And as I told you, you can expand this in the form of combination of cosine and sine. And sometimes, for example, in previous example, when I solve, I use this form A and B, which in that example was C1 cosine omega t plus C2 sine omega t, and then I substitute and find C1 and C2. So you can use any of these forms to find the particular response, to obtain the particular response. But we use this form to study the behavior of the system versus the frequency ratio and the damping ratio in our system. But in the exam, or generally when you want to obtain the response of the system, it's the best option to use this method and consider the particular response in this form and substitute into the main equation and obtain the constant coefficient A and B, or C1 and C2 in the previous examples. Okay, here, if you plot the phase angle phi versus the frequency ratio, here you can see this is the frequency ratio, omega divided by omega n. And also we have plotted this curve for different values of damping ratio. Psi is the damping ratio. Here you can see on this line psi is 0, or this line. And now we want to discuss the behavior of the structure versus the variation of frequency ratio and damping ratio. So the vertical axis, as you can see, is the phase angle phi. The horizontal axis is the frequency ratio, and we plotted these curves for different values of psi, which is the damping ratio. The first conclusion here is for an undamped system when psi is equal to 0, and this line and also this line, on these two lines, the psi is equal to 0, as you can see. And this is in fact for a system without damping or an undamped system. As you can see, the response are in phase when R is less than 1 for this area. The response is in phase with the excitation. And for this area, when R is more than 1, the response is out of phase with the excitation. Of course, we concluded these results in previous section, but here you can again see on this graph. And you know, when R is less than 1, it means that the frequency of the excitation is less than the frequency of the system. And when R is more than 1, it means that the frequency of the excitation is more than the natural frequency of your system. The second conclusion is here, you can see in this area when R is less than 1, or the frequency of excitation is less than the natural frequency of the system, the phase angle is between 0 and 90 degree. Here you can see that the phase angle located in this area between 0 and 90 degree, or pi over 2 degree, which it means that the response lags the excitation. But on the other hand, when the frequency of excitation is more than the natural frequency, or the frequency ratio is more than 1 for this area, you can see that the angle phase is between 90 degree and 180. And if you plot the response and the excitation on one graph, you can see that this behavior means that the response leads the excitation this time. Okay, so these are some conclusions that we can extract from the relation between phi and frequency ratio, and also the damping ratio. And as you can see here, as R is equal to 1, for this case, we have the resonance when omega is equal to omega n, or the frequency of excitation is equal to the frequency of the system, or the natural frequency of the system. Okay. The next one, we can discuss the same results for a system for the amplitude ratio, or the ratio of x, the amplitude of the response, to the static deflection. Here, in this case, if you look at the horizontal axis, again, this is the frequency ratio, the ratio of omega to omega n, the ratio of the frequency of excitation to the frequency of the system. This time, the first important one, the first and the most important conclusion is when R is equal to 1. Here you can see we have the infinity in the M, or in the amplitude ratio. At this area, you can see that the amplitude ratio goes to the infinity, and this is when we have, and of course, when we don't have damping in the system, or psi is equal to 0. So in this case, you can see the resonance. And the second conclusion, here you can see by increasing the psi, or the damping ratio, for example, here is 0.1, then it's 0.3, 0.4. You can see by increasing the damping ratio, you can see that the amplitude ratio M is decreasing. And also the reduction of M, or the amplitude ratio, is very significant in this area when we are close to the resonance area, or when R is close to 1. So when omega is close to omega n, the amplitude ratio will increase significantly. And finally, the last conclusion, that it's very important here, you can see by increasing the frequency of the excitation, or by increasing the frequency ratio in this area, you can see in this area, omega, for example, for this point, omega is about 3 times more than the frequency of the system, or omega is equal to 3.2 times by omega n. For this area, you can see that the amplitude becomes smaller with increasing value of the forcing frequency. So you can see in this area, when your frequency of the excitation increases significantly, the amplitude of the ratio will decrease, and it's to somehow it will goes to 0 sometimes. And the effect of the frequency is more than the amplitude. I mean, for example, consider that you have a system which is subjected to a, for example, 10 Newton force with harmonic sine omega t. If you consider that the amplitude remain the same, I mean remain 10 Newton, and the amplitude of the response is, for example, 2 millimeters, by increasing the omega and the same value of the amplitude of the excitation, you can see that the amplitude of the response will decrease significantly, and sometimes by increasing omega you can go to 0. I mean, you can see that the response will goes to 0 despite the amplitude of the force remain the same. Only by changing the frequency we can decrease the amplitude of the response in your system. So it's very important when you want to uh, justify the frequency. You should consider that by increasing the frequency, you can decrease the amplitude of the response. Okay, any question is clear? Okay. The last point is that when omega, the frequency of the excitation, is equal to this term, omega n times by square root of 1 minus 2 psi squared, which psi is the damping ratio, and omega n is the natural frequency of the system. At this time, we can extract the maximum value for the amplitude ratio. Here you can see this is the M max, or the maximum amplitude ratio. And if you substitute and simplify this omega into the previous slide, into the equation for M, you can obtain this relation between the maximum amplitude ratio and the damping ratio psi. In this case, what's the application of this equation? In this case, we can use this equation in the experimental test. Sometimes you deal with a system. I mean, you have a system and you have the response of the system. You know, of course, I think I explained about this, but I think it's better to remind you again this important point, that in the real world, when as an engineer, when you deal with a system, with a vibrating system in a real world, usually you have the response. Okay, so in fact, you should analyze your system inversely. Here in this course, when you want to solve and you want to analyze a system analytically, you need to obtain the equation of motion and then solve the equation of motion and obtain the response. But in the real world, most of the time you have the response, you have that what is the response, what is the behavior of your response, or your velocity or your acceleration of your system, but you don't have any information about the stiffness, about the damping, about the mass of your system, and you need to obtain these important parameters. You need to obtain the natural frequency, you need to obtain the damping ratio Kasai to extract the equation of motion. So in the real world, you should act inversely from the analytical with respect to the analytical analysis. So here, this equation is very useful when you deal with a real system, when you deal with a real system, and in the real system you cannot obtain an exact value for the damping or an exact value for the stiffness in your system. The stiffness can be obtained using the modal analysis, and in the last chapter I will explain how to find the natural frequency of a system using the experimental test. But damping ratio is another important issue that we need to obtain. This method is one of the useful methods that you can use to obtain the damping behavior or damping characteristic of your system. Because, for example, you deal with a building, you don't know how much is the damping in this building. So you can excite this building, and you can, using the accelerometers, you can extract the response of this building, and then according to the response of this building, you can find the maximum value for the amplitude, the M max. When you have the maximum value for the amplitude or amplitude ratio, then you can substitute into this equation and you can find the Kasai or the damping ratio. So this parameter is very important to obtain the damping characteristics in your system when you don't have any information about the damping of your system. So you can use this equation, and in the analytical analysis, when you have the damping ratio, this Kasai, so you can easily obtain the maximum M or the maximum amplitude ratio. But the main application of this equation is in the experimental test, when you want to obtain the damping characteristic of your system, because most of the time you don't have a damper, you don't have a real damper, and in fact you have some hysteresis damping, and you need to model your damping by with an viscous damping to extract the equation of motion and to do your later analysis. For example, you want to control the vibration of a building, you need to know how much is the equivalent damping for this structure. So you can find this Kasai, and using this Kasai, you can consider an equivalent damping, viscous damping in your system, and then you can extract the equation of motion. When you have the equation of motion, you can do your analysis such as control, and you can, for example, optimize your motion, optimize your vibration and other parameters, okay? Any question? Is it clear? If you don't have any question, I think we can wrap up this session and continue again tomorrow. Any question? Okay, so I will wrap up this session, and again, we will continue tomorrow. And also tomorrow we will have tutorial. Okay, thank you for your attention, and again, see you on tomorrow. Thank you. Bye.